chapter, we will discuss about least cost path analysis, requirement for least cost analysis, creating least cost analysis, working of the least cost analysis, application, proximity analysis. Least cost path analysis is defined by finding the shortest route with the lowest cost associated with it that links any archaeological site or feature in the landscape with another point. Cost can be interpreted in different ways such as time, travel or travel distance, or by including, for example, the metabolic rate of an individual moving and calculating effort. It is based on a cost surface that is derived from a raster grid, a DEM in most cases. Least cost path analysis is a distance analysis tool within GIS that uses the least cost path or the path between the two locations that cost the least to those travelling along it to determine the most cost effective route between a source and a destination. Cost can be a function of time, distance or other criteria that is defined by the user. Least cost path analysis is raster based and has a narrower focus. Using a cost raster that is defined that cost of a moving through each cell, it finds the least accumulated cost path between the cells. When using least cost path analysis in GIS, the 8 neighbors of a raster cell are calculated and the generated path moves to the cells with the smallest accumulated or cost value, that is distance analysis using ArcGIS. This process is repeated multiple times until the source and the destination are connected. The completed path is the smallest sum of raster cells value between 2 points and it has the lowest cost. Least cost path analysis is useful as a planning tool for locating new road or new pipeline that is least costly in terms of construction cost as well as the potential cost of the environmental impacts. Least cost path analysis and shortest path analysis share same common terms and concepts, but they differ in the data format and data analysis environment. Least cost path analysis uses raster data to locate a virtual least cost path. In contrast, the shortest path analysis finds the shortest path between stops on the existing network. Researchers and archaeologists use GIS functions to explore many different topics and answer research questions. They said, therefore, the analyst should make sure that the accuracy of his or her data because results which are not verified and validated could be misleading and inaccurate. Least cost path analysis is an important GIS tool to understand because it has many different applications, all of which can help businesses, city planners and other users save time and money. There exists different sources of variation in generating least cost path and these will produce varying paths depending on the variables that are selected to be manipulated and those that remain constant. However, other sources of variation exist such as the DEM accuracy, the slope algorithms, the cost surface algorithms, the least cost path algorithms. These can all be manipulated individually or simultaneously and would generate different path routes accordingly. The slope and the cost surface algorithm usually dictate the cost unit to be taken into consideration, that is, cost measured in time and in the energy units. Prior to conducting a least cost path analysis, there are some requirements that all users must have and understand. These are a source raster, a cost raster, a cost distance measures and an algorithm for deriving the least cost path. A source raster is a raster that defines the source to which the least cost path from each cell is calculated. This means the source raster is a raster that defines where the least cost path is going and the source cell is the end of that path. In the source raster only, the source cell has a value and all others are given a no data value. Similar to a physical distance measure operations, cost distance measure spread from the source cell, but in the context of least cost path analysis, one can consider the source cell as an end point of the path, either the origin or the destination. Then also is derives for a cell the least accumulated cost path to the source cell or to the closest source cell if two or more source cells are present. The cost raster is the raster that defines the cost or other impedance that is defined by the user. To move through each raster cell, a cost raster has three characteristics. The first is that the cost of each cell is the sum of different costs, while the second is that cost can represent either the actual or the relative cost. The third characteristic is that the cost factor can be weighted depending on the importance for each factor. The cost distance measure portion of least cost path analysis is centered on the node link raster cell representation. In this representation, a node is the center of the raster cell and the link connects the nodes of its neighboring cell. A lateral link is also included to connect a cell to one of its four nearest neighbors, and a diagonal link connects the cells to the corner neighbors. The cost distance is the cost that it takes to travel from the node to these links, and the cost and the least cost path is based on those costs. Finally, least cost path analysis requires an algorithm for deriving a least cost path. An algorithm is an important component of least cost path analysis because accumulative cost between two cells can be calculated by adding the cost of connecting the two cells by least accumulative cost are challenging because there are many different ways to connect two cells and they do not have to be immediate neighbors. Least cost paths are derived after all possible paths are evaluated. Thus, an algorithm makes these complex and time consuming calculations much easier. Once the four requirements for conducting a least cost path analysis are met, it is important to consider and correctly weigh the raster making up the cost raster to create an effective least cost path analysis, that is creating the least cost path. The cost is the factor that is being tested in these analyses, and they can be a function of time, distance or other criteria that the user defines and deems most important. How the cost rasters are weighted depending on the project application and the desired result. Take for example, a least cost path analysis examining routes between two campgrounds. The time it takes to travel between them and the monetary cost of fuel are the two most important costs being tested. The user needs to determine which of these is most important and weight them accordingly. Weighted distance analysis, that is the determination of the best path between the two campgrounds considering time and fuel usage based on terrain, etc., is one of the tools that can be used to help weight the two factors. Distance analysis using ArcGIS. Once correctly weighted, a least cost path analysis between the two is generated based on factors such as speed limits and terrain among others. When creating a least cost path analysis, there is a simple workflow to follow to ensure that the analysis is complete. The first step is the least cost path analysis workflow is to reclassify the value ranges of the raster to make sure that they use a common weighing scale. The next step is to combine the reclassified rasters and create a total cost surface. This step is followed by performing a cost weighted analysis to create cost, the distance and cost direction raster that are required to complete the analysis. The final step in conducting a least cost path analysis is to use the cost distance and cost direction raster as the main input in the cost path tool. This tool then determines the final least cost path from the source to the destination. The least cost path finds the most cost effective path from the starting point to the destination. As it goes from the start to finish, the chosen path accumulates the least amount of cost. This analysis is very practical in linear infrastructure and routing application. For example, pipeline, power line, a trail planning heavily rely on this type of analysis for route selection. How to use the least cost path? There are three main steps when you run this analysis. First, cost distance. First, you have to calculate the cost in relation to your start point. For routing a hiking trail, your cost matrix would be the slope. The higher the slope, the more costly it would be. The second, cost backlink. Second, you need to calculate the raster backlink. In this case, it would be the direction in which the path will go with all 8 possible cardinal directions from one cell to the next. Third, cost path. Finally, you can calculate the least cost path using the cost distance, cost backlink and destination source. No matter which route, any path to the destination equals the same net change in the elevation, but the least cost path accumulates the least amount of slope. Least cost path analysis has a number of different GIS applications. It is often used in planning infrastructure such as roads, pipelines, canals and power transmission lines, as well as recreational uses such as the development of a hiking trail system in the national park. As example, least cost path analysis has been used to locate footpaths in mountainous area, to derive an Arctic all-weather road, to find trail location for all-terrain vehicles. Least cost path analysis can also be used by ecologists to monitor wildlife movements to combat environmental issues like habitat fragmentation. In such studies, the source cell represent habitat concentration areas and the cost factor typically include vegetation, topography and human activities such as roads. Analysis results can show the least cost routes for wildlife movement. Economy and business geographer as well as those making tourist map and guides can use least cost path analysis to determine the best and most cost effective routes between places on delivering routes, national monuments or other destination. Whatever it is, its use, least cost path analysis is an important tool in GIS because it helps the ability to help businesses, city planners and other users save time and money. There are two in-depth examples of least cost path and how it works. One, pipeline routing. If you want to find the most cost effective route for a pipeline, you will likely want to design it where it costs the least. For example, the cost distance layer would include weighted values from population density, environmental sites and proximity to water. Second, hiking trail planning. The cost would be very different from planning a family-friendly hiking trail. In this case, you would want to build it on the least amount of slope so it is safe to climb. As you go from the start point to its destination, you want to buy the lowest cost, which would be the least amount of slope. Any route to the top equals the same net change in elevation, but least cost path accumulates the least amount of slope from start to finished. Proximity analysis is a class of spatial analysis tool and algorithm that employ geographic distance as the central principle. Proximity analysis is a crucial tool for business marketing and site selection. Marketers analyze demographic and infrastructure to determine trade areas. Trade areas are continuous geographic areas around a site that generate a majority of revenue. Proximity analysis is a study using location intelligence, mapping software to calculate the distances between the consumer or the prospect location to your locations, that is the retail store, bank, restaurant, dealer or sales representatives, as a first step in building an understanding of trade sales service areas. An analysis typically includes a report and map showing the relationship of the data and often includes competitor locations in the analysis. There are a variety of tools, models and algorithms that incorporate geographic distance due to the variety of relevant problems and tasks. That said, almost all are fundamentally based on a few core principles of geography, such as the friction of distance and the spatial autocorrelation. The diagram is actually showing a variogram, and you can see different amount of colors is being given for different amount of cost it is being included. Buffers. Buffer is a tool for determining the region that is within a specified distance of a set of geographic features. Cost distance analysis. Cost distance analysis is an algorithm for finding optimal routes through continuous space that minimizes distance and other location depending cost. Voronoi diagram, also known as Tessian polygons, an algorithm for partitioning continuous space into set of region based on a set of point location, such that each region consists of locations that are closer to one of the points than others. Distance decay. Distance decay is based on the inverse square law, a mathematical model of how the influence of a phenomena tend to be inversely proportional to the distance from it. A gravity model is a similar model. Location analysis. Location analysis is a set of usually heuristic algorithms for finding the optimal location of a limited set of points, for example, the store location, that minimize the aggregate distance to another set of points, that is consumer points. A commonly used example is Lloyd's algorithm. Distance matrix. A distance matrix is an array containing the distances, that is Euclidean or otherwise, between any two points in a set. This is frequently used as the independent variable in statistical test of whether the strength of the relationship is correlated with distance, such as the volume of trade between cities. Transport network analysis. Transport network analysis is a set of algorithms and tools for solving a number of distance routing problems when travel is constrained to a network of one-dimensional lines, such as roads and utility networks. The least cost path may be one of the best tools in GIS arsenal for any linear infrastructure and routing application, but the key is that your input data are all logical, accurate and complete. Only then it can determine the most cost effective path, but by accumulating the least amount of cost. Least cost path analysis is considered by many scholars as being a good proxy for studying movement and interaction between the sites in the landscape. Although it is widely used, there are many limitations and challenges yet to be overcome concerning the reliability of the result. The resolution and accuracy of the elevation data used also play an important role in least cost path analysis, and these depend on the topological area being studied. New venues are constantly being sought, and the success of any analysis depends on how the results are compared and tested in concert with data obtained from various sources, and through more visually advanced mapping software purpose.